Hi everyone, welcome to part 1 of chapter 6. Chapter 6 is all about bonding, and today we're going to focus on ionic bonding, or the formation of a bond between a metal and a nonmetal. So you keep hearing this word compounds that I keep using. Most elements, except for the noble gases, are found in nature and combined with other elements. So they don't stand alone typically. We'll typically find them as, part of a compound, like maybe sodium chloride. You might not find it as just sodium or as just chlorine, but we'll see it as sodium chloride, which is table salt. And these compounds are formed when electrons are either transferred or shared to give both atoms a stable electron configuration. And by a stable electron configuration, we mean they have 8 valence electrons, which is why those noble gases don't typically form compounds, because they already have 8 valence electrons. You'll remember the noble gases are all the way over in column 8A, and so they already have a complete octet. So to form these compounds, atoms will either lose, gain, or share electrons, and they will form an ionic bond or a covalent bond in order to obtain an octet. So an octet means, like I said, there will be 8 valence electrons. Ionic bonds are formed when the valence electrons of a metal are being transferred to atoms of nonmetals. So electrons are going from the metal to the nonmetal. The metals are going to lose electrons, and those nonmetals are going to gain electrons, so we are transferring them between the atoms. In a covalent bond, the electrons are being shared, and they will be shared between atoms of nonmetals. So you'll have 2 nonmetals that are sharing their valence electrons. In this lecture today, we are going to focus on ionic bonds. Covalent bonds will be covered more in a later lecture. So here are your examples. When we have, ions, so this one is a positively charged ion. This one is a negatively charged ion. And ions are atoms that are not neutral. So normally, when we were looking at the number of protons, neutrons, electrons in our atoms, we were always saying that they were going to be equal, right? The atomic number told us the number of protons, and protons will equal electrons because it's a neutral atom. Ions are not neutral, okay? So these are atoms with a charge. If it has a positive charge like this, that's telling us that the protons are outnumbering the electrons. If we have a negative charge like this, then that means that the electrons are outnumbering the protons. But either way, this term ion is a general term to tell us that our atom is charged. And when we have these ions, they will make ionic bonds. In molecular compounds, we will make molecules instead of ions, and they will be held together by covalent bonds. And these covalent bonds, again, are going to be the sharing of electrons between nonmetals. So as you can see in this ionic compound, we have sodium is a metal and chlorine is a nonmetal. And in water, we have hydrogen is a nonmetal, and oxygen is also a nonmetal. So here we have electrons that are being shared between 2 nonmetals. It's the same in this molecule of propane here. Carbon is a nonmetal and hydrogen is a nonmetal. So it's a really easy way to see whether something is ionically bonded or covalently bonded, because in an ionic bond, you'll see a metal and a nonmetal. In a covalent bond, you'll see 2 nonmetals. So in an ionic bond, we are getting a transfer of electrons. This metal, right, we're going to say M stands for metal. This metal is going to transfer its electrons to the nonmetal over here, which we're saying is Nm. And when we transfer that electrons, right, that metal has lost an electron, giving it a positive charge. And the nonmetal has gained an electron, giving it a negative charge. And that positive is attracted to that negative, and in that attraction, we will form an ionic bond. A covalent bond is a little different. In a covalent bond, we have electrons that are being shared. So you'll see this nonmetal on the left has 7 valence electrons, and the nonmetal on the right also has 7 valence electrons. If they share this electron, then they will get to 8 valence electrons, which again is the name of the game. That's why atoms make compounds. They're all trying to get to 8 valence electrons. And when they share them, now the nonmetal on the left has 1, 2, 3, 4, 5, 6, 7, 8. And the nonmetal on the right has 1, 2, 3, 4, 5, 6, 7, 8. So they both have 8 valence electrons when those electrons are being shared. So ionic bonds are a transfer of electrons. Covalent bonds are sharing electrons. Okay, so we have transfer versus shared. So when atoms form compounds, they will change their physical properties. Okay, they will change their chemical properties. So if we think about sodium, and we've talked a little bit about sodium and chlorine before, sodium is a soft, shiny metal. It's a silvery metal that you have to store in oil because it reacts with the water in the air, right? We've talked about all of those alkali metals react with water. And then chlorine is a yellow-green poisonous gas. And when this shiny silver metal reacts with this poisonous gas, we get stuff we put on food, right? We get table salt. And so these properties before and after the reaction, right? A silvery metal plus a poisonous green gas makes stuff we eat. And so our properties totally change before and after the reaction, right? After the reaction, the physical and chemical properties are different. It has a different color, it has a different structure, it reacts differently, right? Everything pretty much before and after the reaction is different. So in order to understand what ions are, we've talked about ions, right? And we need to know that the particles that make up the atom have either a positive or a negative charge. The positive and negative charge are opposites, right? They always cancel out. And so typically in a neutral atom, we will have a net charge of 0. Because in this example, we have 1, 2, 3, 4, 5 positives, 1, 2, 3, 4, 5 negatives. So they cancel out completely, and our net charge will be 0. We know that positively charged particle is called a proton, and the negatively charged particle is called an electron. In an atom, we know the protons are in the center, along with, the neutrons, and the electrons are on the outside. I'm going to leave off the neutrons for now, just to make these images a little bit clearer. Only electrons can be added or taken away, right? We know that the number of protons identifies the atom, right? So if we change the number of protons, then we are changing which atom this is. So make sure that you're never changing the number of protons because you're going to change the atom. So only electrons can be added or taken away. So this is an atom with 5 protons and 5 electrons. So the atom right now is neutral. It has a net charge of 0 because the 5 negatives and the 5 positives cancel out, so we have a neutral atom. Now I've added an electron. So what is our charge? Okay, so we have 5 positives and now we have 6 negatives because we've added an electron. So our charge is 1 minus because we have 1 more electron than we have protons, and electrons are negatively charged. So now I've removed some electrons. So if you'll see, we have 5 protons in the middle and 3 electrons around the outside. So we have 2 extra protons. So that means that our charge is 2 plus because we have 2 more protons. We have 2 extra positively charged particles. So when we have something right here, we had 5 protons in the middle and 5 electrons around the outside. And here we have now only 4 electrons around the outside because we've lost this 1 electron. When we are removing electrons, the resulting charge is positive because the number of protons is now outnumbering the number of electrons, right? We have 5 positives and only 4 negatives, so we end up with an overall charge of 1 plus. So the atom now has more protons than it has electrons. Now here we have 5 protons, but now we have, and on the left we had 5 electrons. On the right we have 1, 2, 3, 4, 5, 6, 7 electrons. Okay, so when we are adding electrons, the resulting charge is negative. And so here we're going from a neutral to a 2- because we have 2 extra electrons, and electrons are negatively charged. Okay, so you'll see a negative charge when it has more electrons than it has protons. So either way though, an atom with a positive or a negative charge is called an ion. So atoms without a charge are called atoms. Atoms with a positive or negative charge are called ions. And remember, only the number of electrons can change. Only electrons can be added or subtracted. Remember, the number of protons in an atom never changes, and this is because the number of protons identifies the atom. So if we have, 2 protons, that means that it's going to be helium. If we change the number of protons, say we lost a proton, and now we only have 1 proton, now that atom would be hydrogen. It's a totally different atom. So we can only change the number of electrons when we are forming these bonds. So we have 2 different types of ions, right? So ions are charged particles, but we have different names for the positive ions and the negative ions. So cations are positive ions. And so this is not pronounced cations. This is pronounced cations, like a kitty cat, right? So don't say cations, cations, and they are positively charged ions. And this means that there are more protons than there are electrons. And what you really need to remember is that it happens when an atom loses electrons. And you can think of it, right? Atoms or electrons are negatively charged. And so when an atom loses a negative, it's like subtracting a negative, which makes it positive, if you want to think about it that way. But it happens because there are more protons than there are electrons. And when we're naming the cations, the name will stay the same. So if it was calcium, even if it's now calcium 2+, we're still going to call it calcium. And the way that I remember that cations are positive is I remember that cats have paws, therefore ions with a positive charge are cations. Sorry, bad chemistry jokes. You can also remember it though, if you want. Cations, the word has essentially a plus sign in it, so that's how we know that cations are positive. But I like to remember cations are positive because cats have paws. So here's a cation. So we have a sodium, right? A sodium atom will have 11 protons and it will have 11 electrons because when it's neutral, our electrons and our protons are always equal. Now sodium, to form an ion, will lose an electron here. And when sodium loses an electron, it becomes Na+. And so now it is a cation, right? It has more protons than it has electrons. It has 11 protons, and now since it's lost one, it only has 10 electrons. And so now it becomes Na+, which we call sodium. If we look at the electron configuration, right, we have to see how this losing an electron gives us 8 valence electrons. Because it's really easy to see it with the nonmetals, that we'll talk about it in a minute, but it's a little bit stranger to see it with the metals. So if we look at the electron configuration for sodium, right now, sodium has 1 valence electron. It has 1 electron in its outer shell. When it loses that 1 electron, now it's going to lose, right? It's going to lose that 3s1 electron. And when it loses it, it now is left with our second energy level as our outermost energy level. And if you look though, in this outermost energy level, we have 2 plus 6 electrons in that outermost energy level. So when we lose that 3s1 electron, we now have 8 in our outermost energy level. I'm going to show you this on a Bohr model too. So let's say this is our nucleus for now, because our protons don't really matter for this example. But if we look at our electron configuration here, right, we're going to need 3 energy levels, right, because the 3 in the front is the largest number. So we'll draw our 3 energy levels. So there are 2 electrons in the first energy level, and then we have, right, from here, and then we have 2 electrons in our second energy level, plus another 6 in our second energy level. And then we have 1 in our third energy level. Okay, so that would be a neutral sodium atom. If the sodium loses one electron, it's always going to lose it from the outermost energy level. So it's going to lose this 3s1 electron. And when it loses that electron, now it looks like this over here. So we have our nucleus, and we only have 2 energy levels because we've lost that 3s1 electron. So that third energy level goes completely away. So now we have 2 electrons in the 1s, 2 electrons in the 2s, and 6 electrons in the 2p. So now when sodium loses that 1 valence electron, loses that 3s electron, it has 8 electrons in its outermost energy level because it's lost that entire, third energy level. Okay, so this is how making that cation gives sodium an octet. So now just remember, positively charged ions of metals are called cations because cats have paws. So here's another example. So we have magnesium is a metal in group 2A. So we talked before about sodium. Sodium was in 1A, right? It's an alkali metal. Magnesium is in group 2A, and it will form a stable electron configuration by losing 2 valence electrons. So if we look at this, our electron configurations here, magnesium has 2 electrons in the 3s. So in order to get down to that second energy level that we know has 8 valence electrons, it needs to lose both of these. Okay, so sodium only had 1 valence electron, right? One electron in the 3s, so it only needed to lose that 1 electron to get down to having, that second energy level that was full. Magnesium, since it has 2 valence electrons, it will need to lose 2 in order to get down to that next level. So again, let's look at the, at the Bohr model here. So we have our nucleus, we have 3 energy levels, and this is going to look very similar to sodium, right? So we have 2 electrons in the 1s, we have 2 electrons in the 2s, we have 3 electrons in the 2p, 6 electrons in the 2p, and then we have 2 electrons in that 3s orbital. Okay, so now it's going to lose both of these valence electrons in order to get that second energy level to be its outermost energy level. So when it does that, then it will have its nucleus, right? And now it will only have 2 energy levels because it's lost all of the electrons in the third energy level. So we have 2 electrons in the 1s, 2 electrons in the 2s, and 6 electrons in the 2p, which will give us 8 valence electrons. So magnesium will lose 2 because it's in group 2A. So a pattern will start to emerge here. If it's in group 1A, it will lose 1 electron and form a +1 or a 1+ charge. If it's in group 2A, it will lose 2 electrons and form a 2+ charge. If it's in group 3A, then it will form, will lose 3 electrons and form a 3+ charge. And these are most of the ones that will make the positively charged ions. Those are most of the metals. Then we start to get into the nonmetals that will form negatively charged ions. So anions are what we call negatively charged ions. Okay, this happens when there are more electrons than there are protons. And this will happen when the atom gains electrons. Okay, so when it gains electrons, the electrons will outnumber the protons, and then it will be negatively charged. We will change the name of the anion to end in IDE. So like if it was chlorine, it becomes chloride, or if it was fluorine, it becomes fluoride, or oxygen becomes oxide, right? We are always going to change it to end in IDE. And you can remember that it's negatively charged when it gains electrons because you can think, if you're adding a negative, that's still a negative. But it really happens because there are more electrons than there are protons. And I don't have as cute of an example for this one, like the cations, because cats have paws. You can remember anions then are just the other ones. That means they're negative. Or, and this is kind of a stretch, if you put a negative ion, if you write down a negative ion and you mush it all together and you cross out the negative, then you get anion. I told you it's kind of a stretch. you can also remember, because a lot of people will mispronounce this as anions, but it's not, it's anions. But it kind of looks like onions. You can think about if you have onion breath, then that's a negative thing, right? People don't want to be close to you. That's the only thing I got. So otherwise, I would remember cations are positive because cats have paws, so anions are the negative ones. So if we look at our anions, right? Our negative ions, the ones that have gained electrons. This is going to happen with the nonmetals, okay? So if we look at chlorine, chlorine has 17 protons and 17 electrons. And when it gains an electron, it will now have 17 protons still, but it will have 18 electrons. So our negatives are outnumbering our positives, therefore this atom will have a negative charge. If we look at the electron configuration again, right, just like we were doing in the last one, we can do the Bohr models to see how this is giving us 8 valence electrons. So again, I'm just going to draw a circle for our nucleus for now. And so we have 3 energy levels because a 3 in the front is our largest number. So we have 2 electrons in the 1s, 2 electrons in the 2s. We're going to have 6 electrons in the 2p. And then we have 3 electrons in the 2s and 5 electrons in the 3p. Okay, so right now, this has 7 valence electrons. Okay, and remember the name of the game is to try and get to 8. So if it has 7 valence electrons, you can think about it as having 2 options, right? It could lose all 7 of those electrons like we saw with the metals, but that would be a lot of electrons to try and give away because the electrons have to go somewhere, right? They would have to be transferred to somewhere. So rather than losing those 7 valence electrons, it's much easier for the chlorine to just find 1 electron to gain. And when it gains that 1 electron, it's going to add it to this 3p, right? Because the 3p has 1 open spot. And so it will form this ion over here, this anion. So we'll draw our nucleus in the middle. And again, we're still going to have 3 energy levels. And then when it gains that electron here, it goes from being 3p5 to 3p6. And so if we were to fill this all in, right? Now we have 6 electrons in our 3p, which gives us a total of 8 valence electrons now. So when chlorine gains an electron, now it has 8 valence electrons. So again, I think it's a little bit easier to see this with the nonmetals than it was with the metals because it's just going into that valence shell. And remember, negatively charged ions of nonmetals are called anions. So chlorine was in group 7a, so it gained 1 electron to get to 8, because we know if it's in group 7a, it has 7 valence electrons, so it just needs to gain 1 more to get to 8. There's another pattern here, and I'll talk about it before we go to the next slide. So if it was in group, 5a, that would mean it has 5 valence electrons, and it would need to gain 3 electrons to get to 8. So it's going to form a 3- charge. If it's in group 6a, then it has 6 valence electrons. It will need to gain 2 to get to 8, so it will end up with a 2- charge. If it has 7 valence electrons, like chlorine in this example, then it will only need to gain 1 to get to 8. Okay, so again, we're seeing a pattern here. So this is just kind of a summary. If it's in group 1a, it will always form a 1+ cation here. If it's in group 2a, it will always form a 2+. Group 3a's will form a 3+. And then we're just going to leave off 4a for now. 4a is carbon, and it will typically do, and some other things, but carbon is the one that we're going to use the most, and it will do a different type of bonding usually. It will typically do covalent bonding, not usually ionic bonding. So we're going to go ahead and leave it out for now. So if you see that I'm skipping the 4a, that's what's happening. We'll talk about some of the 4a, the bigger ones like lead, next time. For now, just don't worry about the 4a. So we've got 1a, 2a, 3a, that's going to make 1 + 2 + 3+. And then for the anions, we have 5a, which like I said, means that we have 5 valence electrons. So they are going to gain 3 to get to 8, so they will form a 3 minus. Group 6A has 6 valence electrons. They're going to gain 2, so they're going to make a 2 minus. And our group 7A will gain 1, and they will make a 1 minus. So if we're looking at the periodic table, and this is going to be my sketch of the periodic table here. If we look at group 1A, they're all going to form a 1 plus. Group 2A will form a 2 plus. We're going to go ahead and skip these guys in the middle for now. Group 3A will form a 3 plus. We're going to skip group 4A for now. Group 5A will form a 3 minus. And then group 2A, I'm going to run out of room, will form a 2 minus. Group 5A will form a 3 minus. Group 6A will form a 2 minus. And group 7A will form a 1 minus. I'm just going to go ahead and extend this over here. I'm sorry, guys, this got messy. And group 8A will not form compounds because they are noble gases. So we have, the pattern is 1 plus, 2 plus, 3 plus, skip, 3 minus, 2 minus, 1 minus, skip. Okay, if we're thinking about group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So there's your pattern if you want something to memorize, but this is the rationale behind it, right? All of the metals, all of the ones that form positively charged cations, when they lose their valence electrons, they have a complete shell underneath, like I was showing you with sodium. The nonmetals will gain electrons to complete that valence shell that they already have going. Like I said, group 4A are mostly going to do, or at least the carbon will do covalent bonding, and group 8A, those noble gases typically don't form compounds because they already have 8 valence electrons. So again, atoms will lose or gain electrons, and essentially they will become like their nearest noble gas. So the metals will lose their electrons to go backwards to get the noble gas configuration of the noble gas that came before it, right? Because we know noble gases always have 8 valence electrons. The nonmetals will gain valence electrons to become like their nearest noble gas, okay? Because again, we know that all of the noble gases have 8 valence electrons. They have complete octets. Okay, so if you ever forget, should an atom lose or gain electrons, you can just see, which one, which noble gas is it closest to, and how many electrons do I need to gain or lose to get there. So again, we can use the numbers or the group numbers to tell us the charges of the ions. So you'll notice, again, we skipped group 4A because we're going to talk about them more in covalent bonding. We've skipped group 8A because they already have a complete octet. But otherwise, our group 1 through 3A, they will form positive charges, and group 5 through 7 will form negative charges. So go ahead and find your Chapter 6 lecture worksheet and complete problems 1 through 9 to get some practice on this. Once you're done, come back and we will keep going. Okay, so now we are going to start talking about ionic bonds. And in ionic bonds, we're having an exchange of electrons, right? Electrons are being transferred from the metal to the nonmetal. So that's why Mr. Ionic Bond here says that he has his electrons taken, not shared, right? The sharing of electrons we will talk about when we get into covalent bonds a little bit later. So here's a little bit of vocab for you. So we have ionic bonds are bonds that are formed by the transfer of electrons from a metal cation to a nonmetal anion. And although they are composed of ions, right, they're composed of all of these positive and negative charges, ionic bonds themselves are neutral because the charges of the ions will cancel out. Those positives and negatives will be exactly equal, and we will get a neutral molecule. And then when we talk about chemical formulas, those show the types and numbers of atoms in a molecule of that substance. So like if we were talking about water, right, H2O, that's telling you that there are 2 hydrogens and 1 oxygen. So that is the chemical formula of water. So So the octet rule we've talked about a little bit already. In forming compounds, atoms tend to achieve the electron configuration of a noble gas, right? And this means that they will have 8 valence electrons. So atoms will either lose, gain, or share electrons in order to have 8 valence electrons. So here's our rules for naming ionic compounds. The name of the cation will always be written first, followed by the anion. The cation is whatever you see on the periodic table. So the metal, right, that metal cation is always going to stay the same. The name of the anion is going to change to end in IDE. So if we have NaCl, right, our metal, our sodium, that comes first. We're going to leave the name of the sodium the same. But the chlorine is going to change and become chloride. And so we're always going to change the name of the nonmetal. So we call this sodium chloride. So let's look here. So we have Ki, right? So our metal is our potassium. Its name will stay the same. The nonmetal is our iodine, so it's going to change to be iodide. In this next one, magnesium's our metal. Its name stays the same. Bromine is our nonmetal, so bromine becomes bromide. Aluminum's our metal. It stays the same. Oxygen becomes oxide. So we're always going to change the name of our nonmetal ion to change into IDE. So go ahead and pause here and try to name these compounds. Once you're ready, unpause, and then we'll go over the answers. Okay, so this first one, this is lithium bromide. So again, we're changing the bromine to end in IDE. This next one will be magnesium chloride. So again, we're changing chlorine to end in IDE. This will be aluminum sulfide. That sulfur becomes sulfide. This one is aluminum chloride. Oops. And then the last one is magnesium sulfide. Okay, so again, the names of the metals all stay the same. The name of the nonmetals will change to end in IDE. I left this note here at the bottom because this will be important later. For naming ionic compounds, it doesn't matter what the numbers on the bottom are. Like, it doesn't matter that there's a 2 here, or this 2, or this 3 here. It doesn't matter at all what those numbers are when we're naming it, but it will when we talk about covalent bonds. So when we talk about covalent bonds, the numbers on the bottom will matter. So I'm telling you this now, that for ionic bonds, it doesn't matter what the numbers on the bottom are. Okay, go ahead and pause here and complete Chapter 6 lecture worksheet, problem number 10. Okay, so now we're going to learn how to write the chemical formula. The chemical formula is a little bit trickier than the name, so we're going to spend a little bit longer on that. The chemical formula, like I talked about earlier, shows the lowest whole number ratio. So like H2O is a little bit different because this is a molecular compound, but this is telling you there are 2 hydrogens per 1 oxygen. So like when we talk about sodium chloride, this is telling you that for every 1 sodium, you have 1 chlorine. And if you had aluminum sulfide, this is telling you that for every 2 aluminums, you have 3 sulfurs. So it's telling you the ratio of the atoms, okay? But they're always in whole number ratios. Like you're not seeing something that has, hydrogen and oxygen, and you just have a half of one. Like you can't do that. Okay. The sum of the ionic charges is always 0. Okay. That means that the charges will always balance out. We're always going to make sure that our positives equal our negatives to get an overall charge of 0. So here, when sodium gives its electron to the chlorine, it forms Na+, and chlorine forms Cl-. But that 1+ is added to that 1- to get an overall charge of 0. If we had 2 sodiums and only 1 chlorine, then they wouldn't balance out because you would have 2 positives and only 1 negative. So our positives and our negatives will always be equal when we're forming ionic compounds. So in this example, we have magnesium, and magnesium had 2 valence electrons. So it's going to lose those 2 valence electrons so that it can, access that complete shell underneath. When it loses those 2 valence electrons, it forms a 2+. So we can't have just one chlorine to balance it out because chlorine is only a 1-. So then we would still have a leftover 1+ charge. So we need 2 chlorines to balance out the charge. So now we have magnesium is a 2+, and we have 2 1- to balance it out. So we have 2 positives and 2 negatives now to get an overall charge of 0. Okay, because our ionic compound has to be neutral. It has to be balanced out. So we'll always have our positives equal our negatives. So here's how we're going to write the formulas for ionic compounds. You're going to write the metal ion followed by the nonmetal ion formula. And then you're going to combine the smallest whole numbers of each ion to provide an overall charge equal to 0. And I use this rule, circle and switch, which I will show you how to do that. And then when you're figuring out the formula for the metal and the nonmetal, you're going to use subscripts, okay? And you're going to figure them out in step 2 for each ion. So the way that it looks like is this. You might have an example or a problem that says, write the chemical formula for barium nitride. The first step would be to write the formula for the metal and nonmetal ions. So barium is in group 2A, so it's going to lose those 2 valence electrons, and it's going to form a 2+. Nitrogen is in group 5A, so it's going to gain 3 valence electrons and form a 3-. Okay. Again, make sure you're, thinking about it where barium has 2 valence electrons, so it's easier for it to lose 2 to get to that nearest noble gas, right? It's going to lose the 2 in its outer shell to get to that complete shell underneath. Whereas nitrogen, it's easier for it to get to the nearest noble gas by gaining 3, so it will form a 3-. Okay, so that's how we're going to figure out these charges. Now, figuring out the ratio is not as straightforward when we had like magnesium chloride, right? When we had magnesium had a 2+ and chlorine was a 1-. So it was easy to see that we would need to have 2 chlorines to balance out that 2+ charge from the magnesium. Here it's not as straightforward, right? Because, we have a 2+ and a 3-. So we're going to do this thing that I like to call circle and switch. Okay, so if the charges are not equal with opposite signs, so that's telling you if it's not something like barium and sulfur, right? Where they both have a 2, but they're just opposite, right? They always have to be opposite. We have to have a metal lose its electrons and give it to a nonmetal. But if the numbers, right, if their numbers are the same, then they're going to exactly cancel out, and we don't need to do this last step. But here we have barium, which is a 2+, and nitrogen is a 3-, so the charges aren't equal. So we're going to circle and switch to find the formula. So we take our numbers and we're going to switch them. Okay, and then we're going to write the formula. So the 3 from the nitrogen now becomes, this 3 from the nitrogen now becomes the subscript for the barium. And the 2 from the barium now becomes the subscript for the nitrogen. So this becomes Ba3N2. Okay, when you circle and switch, make sure do not take the charges. You're just taking the number with you. So the 3 from the nitrogen goes to the barium, the 2 from the barium goes to the nitrogen, and we're getting this formula at the bottom. And we can prove that it cancels out because if we have 3 bariums, right, plus, 2 nitrogens, we need that to equal 0. Well, 3 bariums, each barium was a 2+, and we have 2 nitrogens, and each one was a 3-. So we're getting 6+ over here, plus 6- gives us a 0. Okay, so that's how we know that this is the right formula. Okay, so this circle and switch will help you out a lot when we're trying to figure out how to make our compounds neutral. Let's try some more. You can pause here if you think you've got it, or you can watch a couple and then pause and try some on your own. So the first step is to always write out the ions. Okay, so potassium fluoride. Potassium is in group 1A, which means it makes a 1+. Fluorine is in group 7A, which means it makes a 1-. So now the the 1 plus versus the 1 minus, those are going to exactly cancel out because they are equal and opposite. So we don't need to do the circle and switch method. We can just mush them together because that 1 plus will equal the 1, or will cancel the 1 minus out. So we're going to get Kf. We can just combine them directly. Magnesium is in group 2A, so it's going to form a 2 plus. Sulfur is in group 6A, so it's going to form a 2 minus. So again, the charges here are exactly equal and opposite. They're both 2s. So that 2 plus from the magnesium is directly going to cancel out that 2 minus from the sulfur, so we don't need to circle and switch. We can just put them together. Sodium oxide. Sodium is in group 1A, which means it has 1 valence electron. It's going to lose it and make a 1 plus charge. Oxygen is in group 6A, which means it has 6 valence electrons. It needs to gain 2 more to get to 8. So now here our charges are not equal and opposite. We have a 1 plus versus a 2 minus. So we can circle and switch. So the 2 from the oxygen is going to go to the sodium. So we'll get Na2. That imaginary 1 from the sodium is going to go to the oxygen. So we'll get O. And we don't write 1s because they're redundant. So the 2 from the oxygen went to the sodium. The imaginary 1 from the sodium went to the oxygen, so we got Na2O. Calcium nitride. Calcium is in group 2A, so it forms a 2 plus. Nitrogen is in group 5A, so it has 5 valence electrons. It gains 3 and becomes a 3 minus. So now again, our charges are not equal and opposite, so we're going to circle and switch. So that 3 from the nitrogen will go to the calcium, so we will get Ca3, and the 2 from the calcium will go to the nitrogen, so we will get N2. Okay, so again, the 3 from the nitrogen went to the calcium, and the 2 from the calcium went to the nitrogen, which made us Ca3N2. Lithium phosphide. Lithium is a 1A, so it forms a 1 plus. Phosphorus is in group 5A, so it forms a 3 minus. So again, we need to circle and switch because our charges are not equal and opposite. So that 3 from the phosphorus is going to go to the lithium, so we get Li3, and that imaginary 1 from the lithium will go to the phosphorus, so we get P, and remember we don't write 1s because they're redundant. And then lastly, we have magnesium fluoride. Magnesium gets a 2 plus because it's in group 2A. Fluorine gets a 1 minus because it's in group 7A. Our charges are not equal and opposite, so we're going to go ahead and circle and switch. So our imaginary 1 from the fluorine will go to the magnesium, so we get Mg, and we're not going to write the 1. And then the 2 from the magnesium will go to the fluorine, so we get F2. Okay, so our rule is circle and switch if the charges are different. I want to make a note here. Say that you hadn't noticed on magnesium sulfide and you'd written this Mg2S2. What I want you to notice, if you ever do that, do you see that there are both 2s? That means that we need to reduce this. We need to write it in a lower ratio. And so you would divide both of those subscripts by 2 and you would get Mgs. So if you ever do this accidentally, just notice that they can both be divided by 2 and make it, the correct compound. So go ahead now and complete lecture worksheet problems number 11 through 17 to get some formula on writing these ionic compounds. They're a little bit tricky at first, and they will require some practice. So make sure you are practicing. And you also need to be able to remember, what ions things are making. You need to know if something is in the group 2A, right? If it's an alkaline earth metal, then it's always going to form a 2 plus. You need to know that. That's not going to be provided to you. So start working on those ions and forming ionic compounds. You need to get really, really good at this now because our next lecture will build on these skills we've talked about today, and we're going to make it even more complex. So do lecture worksheet problems number 11 through 17 and get a lot of practice. Okay, now our last little bit for today is to introduce these polyatomic ions. Polyatomic ions are poly, meaning many, atoms that are charged. So we have many atoms together that are charged. So there's more than one atom bonded together that has a charge on it. These are all going to be covalently bonded. They're all going to be nonmetals. But they're, when they bond together, they are not neutral. They have an overall charge. So like this one, this first example, this one, HCO3, 1-, that is bicarbonate. Okay, so these are all polyatomic ions, and you get to memorize them. Yay! There are a lot more. This is a very short list of polyatomic ions. What I would recommend that you do is make flashcards. You need to be able to know these kind of like you know the elements for the element quiz. So if I write down bicarbonate, you need to write down HCO3, 1-, or if I write down hydroxide, you need to write down OH-. Okay, be very careful when you are memorizing these to figure out which numbers are subscripts and which numbers are superscripts. Okay, which numbers go on the bottom and which numbers go on the top. So like bicarbonate is HCO, that 3 is on the bottom, the 1- is up on the top. Okay, so the charges are always going to be up high, and the other things will be down low. So be very, very careful when you are memorizing things that you figure out, where they're going. Don't write it all as HCO3-, because that would mean something different. Okay, but the reason I'm telling you about these now is that we are going to use these polyatomic ions in the next lecture. So it's really helpful if you start memorizing them now, so you're not continually needing to look them up. In addition, you also have a polyatomic ion quiz that is coming up in the future. So you need to start memorizing them so that you don't try and cram the night before. This is not a good topic to need to cram because some of them are really similar, like nitrite versus nitrate. Nitrite has NO2 1- and nitrate has NO3 1-. And then sulfite and sulfate. Here, the difference is, just to kind of help you out, anytime you have something that says ite versus ate, ite will always have one less oxygen than the ate, but the charges will be the same. So nitrite has 2 oxygens, nitrate has 3. Sulfite has 3 oxygens, sulfate has 4. So that's just kind of to help you out. And I remember that nitrite, or the ites, are the ones that are smaller, because like ite, like it sounds little like ite. Anyway, there you go. If that helps,